An archaeologist is flying on board a blimp over a vast, dry, uninhabited desert. With no warning, an angry ticketing officer walks over and asks to see the archaeologist's boarding pass. With nothing to show, the angry ticketing officer quickly takes action, grabbing the man by the arm, opening the window, and throwing him out of the aircraft as he falls 800 meters to his death. Instead, the archaeologist fashions his tweed jacket into a makeshift parachute and slows his fall to a comfortable landing. With one problem. He finds himself in the middle of a vast desert with no sign of life and no way out as the blimp slowly floats out of sight. Out of the corner of his eye, the archaeologist sees a structure in the distance, poking out of the sandy plains. Walking over, he finds the wooden remains of an old building. With no prospects of survival and no water in sight, he gets to work to interpret and estimate the date of which this structure may have been built. This is scientific dating. Considering time is at its core the basis of which all modern archaeology is founded on. Without an understanding of time, there is no definition for an archaeological time frame. But how do you define time? Do people define the passage of time differently? Do the differences in our perception of time influence the way we record history? How can we create a timekeeping mechanism? And how do we refer to time? These are all fundamental questions of physics and philosophy that require thought if any sense of scientific archaeological time frame is to be built. But when it comes to the lonely desert archaeologist, the concept of time is often referred to as a chronology, best defined as the order in which a series of events happen. Without chronologies, there is no concept of a timeline. Different chronologies are used in different contexts. For example, we are all familiar today with the calendrical system, spanning a few thousand years, which refers to time through the periodic movement of Earth around the Sun. Or perhaps the geological timeline, which spans 4.5 billion years, dating back to the creation of the Earth. However, the key axis that differentiates all archaeological chronologies is the distinction between the absolute and relative chronologies, the distinction between an interval system like the Earth's movement around the Sun against an ordinal system like the historical record of events. Relative chronologies are the oldest in archaeology, placing events or artifacts in a linear sequence without assigning any specific dates. This is useful to determine the order in which events occurred through time relative to one another. The most famous example of such a chronology is known as a stratigraphy. Sediments accumulate over time to create layers called strata, and just like looking deeper into the stars brings you further back in time, the deeper you dig, the older it gets. This is known as the law of superposition. Absolute chronologies, on the other hand, provide specific dates and points in time, allowing for a precise understanding of when something occurred. Up until the 20th century, the only way of getting absolute dates was through historical records, or artifacts with specific dates on them, like coins or an inscription of some sort. This all changed with the invention of scientific absolute dating in the 1950s, as the archaeological applications of radioactive decay were realized and a plethora of new dating technologies were invented in the years to follow. The archaeologist walks up to the structure made of wood and determines there is no date, no engraving or any sign of historical absolute dates. To accurately date the wooden structure, he must employ some form of scientific dating. More specifically, the use of dendrochronology, or tree ring dating. Dendro, meaning tree, and chronology, meaning the study of time, is based on two fundamental principles. Number one, some species of trees grow annual rings, meaning if you were to count each one of these rings, you could infer how long the tree has lived. Number two, the width of each tree ring is driven by changes in climate and local environment. These principles allow us to date annual tree rings to their exact year of formation. This date will correspond to the date that the tree was cut down. This is called the dated event in archaeology, where a specific occurrence or moment in time has been assigned an age based on the method that was used in the dating process. To determine the age of a wooden structure, our archaeologists first must extract a core sample of wood from one of the beams. These pencil-thin core samples are then polished to look at under a microscope, and each ring is counted and measured to an accuracy of at least 1/100th of a millimeter. By comparing the growth patterns of different samples from the same region, it is possible to establish a chronological sequence, matching the average variations in ring patterns from different trees. This process is called cross-dating. A unique pattern of wide and narrow rings formed during a 50-year period is unlikely to be formed during any other 50-year period, because climate varies from year to year. From this, archaeologists can develop a master chronology for any specific region, cross-dating numerous old and new sample trees to form one long continuous chronology, some of the longest dating back to almost 12,000 years. Our archaeologist can then match up his core sample to the master chronology and deduce its approximate age. Any given sample requires at least 100 rings to get a match, so the longer the tree lives, the better the sample, for example pine and oak trees. Samples can be taken from house beams, shipwrecks, preserved wood, and even musical instruments. like a Stradivarius violin known as the Messiah violin, which was used to date. Generally speaking, its trees is the margin of their acceptable habitats that have the most variation in ring thickness, and are therefore easier to match to a chronology. So if you have a tree on flat ground getting a regular amount of water and nutrients on an annual basis, its rings will look very regular, like this, which gives you little to no information. But if you had a tree maybe on a sloping hill that doesn't usually grow there, with large variations in rainwater and wind and sunlight, its rings will look like this, which is much easier to match up to a timeline. Tree rings can be split up into three categories: the bark, which is the outermost layer of a tree, the sapwood just beneath the bark representing the part of the tree that is still alive, and the heartwood at the center. For a sample to be accurately dated, it should ideally contain bark, which can then be dated to the season it was cut down, or the sapwood, which can be dated to an accuracy of plus or minus 8 years. If a sample only has heartwood, only a maximum age can be deduced. This is all assuming that the structure was built at a similar time to when the tree that its wood came from was cut down. Unless matched up with the present day, Dendrochronology cannot always be considered an absolute dating technique, but was fundamental to the development of later methodologies. The archaeologist decides that to gain a better grasp of his situation at hand, he must dig down into the ground further into the past. As he digs, he stumbles upon the remains of an old fireplace or hearth, with several burnt pieces of charcoal and bone. To determine the age of the hearth, he must now employ the use of radiocarbon dating. To understand carbon dating, we must first understand that every living thing is made of carbon. Plants absorb carbon from the atmosphere and use it to support their growth. Animals then come along and eat these plants, in turn consuming quantities of the original atmospheric carbon. The key lies in the other stuff. Approximately 99% of carbon nuclei consist of 6 protons and 6 neutrons. This is known as carbon-12. But every now and then, high up in the stratosphere, nitrogen-14 atoms are bombarded with high-energy cosmic particles. This collision, called a spallation reaction, will produce neutrons, which in turn collide with other nitrogen-14 particles, causing it to eject a proton and transform into carbon-14. This carbon-14 isotope is then incorporated into all living organisms. Over time, the ratio between carbon-12 and carbon-14 in the atmosphere remains relatively constant. But this carbon is unique from carbon-12, as it is unstable. At some point in time, it will undergo a process known as beta decay, in which a neutron turns into a proton via the fundamental weak nuclear force, and a single electron is expelled from the atom, adjusting for the charge imbalance, becoming nitrogen-14 once again. So once any living thing dies, its intake of carbon stops, and the carbon-14 already in its body will start to decay. This is radiocarbon's dated event. This decay happens at a fixed rate, where half of any given sample of carbon-14 atoms will undergo beta decay after exactly 5,730 years. This is known as an isotope's half-life. So after 1 half-life, you will have half of the original amount. After 2, you will have a quarter. After 3, an eighth, and so on. The key here is that while the carbon-14 decays, the quantity of carbon-12 stays roughly the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many years have passed since the animal died. Eventually, you will hit a wall at around 50,000 years, where there is too little or no carbon-14 left in any specific sample, and a ratio can no longer be reliably measured. This is called the theoretical limit, and it is here where carbon's usefulness ends and isotopes with longer half-lives must be used to date older samples. For our desert archaeologist, to get a date from this fireplace, he must take a sample of the organic material, either the charcoal or the bone will do. Anything with carbon that was once alive can be dated. This includes wood, bone, shells, leather, coral, and even whiskey has been dated with radiocarbon. A single fragment is preferred to avoid variations in inbuilt ages, which are various discrepancies between the object's dated event and the time frame in which it was used. A typical sample size is of the order of 1 milligram of carbon, which is large enough to avoid the theoretical limit of old samples, where there may not be that much of the C14 isotope left to detect. There are 2 methods our archaeologists could use to detect C14. Today, it is generally done with the use of an accelerated mass spectrometer, which counts the individual atoms using large magnets and detectors and compares the ratio of both carbon isotopes. In the 1950s, Willard Libby's original method of counting C14 was to use a Geiger counter to detect the beta particles released by the isotope's decay. This method, while revolutionary, was less precise and would require sample sizes of an order of about 1,000 times higher than AMS needs. But there's a problem. There's every chance that changes in levels of C14 weren't due to radioactive decay, in which case this would skew the ages of the dated event. So how do we check for this contamination? Luckily for us, most of these sources of contamination like fungus, humic acid, and glues have been identified for and can be treated for in the lab. There is also the assumption that the levels of C14 in the atmosphere have also stayed consistent, which is definitely not true. Things like the Earth's magnetic field, massive water reservoirs like the ocean introducing new carbon in various places, and even fossil fuel burning can vary drastically the amount of carbon present in any one location. Today, all samples are calibrated to these changes in carbon levels using what's called a calibration curve. From this, we can still get accurate age ranges. The archaeologist is intrigued by the presence of a wooden structure on top of a fireplace and decides to keep digging. To his surprise, he finds an almost perfectly preserved grave with a skeleton complete with bones, teeth, and burial goods like pieces of fired pottery. Now, carbon dating could certainly be used to date the skeleton, which would give us a time of death for the individual, but what about the pottery? It doesn't help to use radiometric dating and find out how old the clay is, because this does not tell us when it was formed and used by humans, but instead tells us the date of the clay itself. It is the date of the human interaction with the ceramics that we are interested in. In the 1960s, the first form of something known as trapped charge dating was applied to archaeology. Trapped charge dating relies on the principle that over time, minerals such as quartz and feldspar are exposed to natural background radiation from their local environment and their own radioactive contents. This radiation causes electrons to be ejected from their atoms. As they are ejected, they are trapped in small defects within the mineral's crystal lattice called electron traps. Normally, minerals on the surface are exposed to sunlight. Photons from the sun interact with the trapped electrons, providing them with enough energy to break free from their defects. But if for some reason these mineral deposits were buried and left undisturbed, like an archaeological site for example, these trapped electrons, instead of being released, start to accumulate. The longer the mineral is buried, the more electrons are trapped. This is the basic principle behind trapped charge dating. When it comes to collecting a date from a sample, there are three main different ways to do this using this concept. As it turns out, light isn't the only thing that releases these trapped electrons. Temperature does as well. When a mineral is heated, the accumulated trapped electrons are released, effectively resetting the luminescence signal for the electrons to accumulate once again. This generally happens at around 500 degrees Celsius. If we can find an object that we know has been heated, then by measuring the mineral's luminescence, we can work out how long ago it was made. This heating is therefore considered the dated event. The amount of light minerals emit is proportional to how long it's been since they were last heated up, like when they were first made. So unlike carbon dating, where the radiation lost gives us an indication of age, here we are looking for the energy that has accumulated since the dated event. Of course, this is assuming that in between the date the artifact was first made and now, there have been no other heating events. To date any given sample, we can reheat it to release all of the trapped electrons, and based on the amount of luminescence, we can determine how much energy has been trapped over the years. This gives us the amount of radiation. With the same sample, we can heat it up enough to reset its electron traps, and expose it to radiation once again to figure out how readily the electrons got trapped in the first place. This is called the dose rate. Then by dividing these two results, we can determine the last time the piece of pottery was heated. What this means though, is that once the given sample is reset, it cannot be dated again, since all the relevant radiation signals will be gone. This method requires the sample in question to have been heated at a given relevant time to work, such as bricks, ceramics, burnt flint, and even burnt soil from hearths. Eventually, the electron traps, if kept undisturbed for long enough, will fill up completely. This on average takes around 200,000 years. So any sample taken from older than 200,000 years, when heated up in a lab, will give off the same maximum luminescence signal. Therefore, anything older than 200,000 years cannot be dated using this method. When dating, larger, well-preserved and homogeneous samples will tend to give better results. As long as there are crystals, electron traps can be measured. Although less precise than radiocarbon, sitting comfortably still with a precision of 5 to 10%, trapped charge dating often finds itself useful when no other option is available. And seeing as archaeologists are always dealing with an inordinate amount of pottery, being able to accurately date when it was made is a very valuable tool. Now, largely the same idea and concepts can be applied to another similar dating method known as optically stimulated luminescence, or OSL. Just as electron traps are reset through a heating event, the same thing happens when quartz and feldspar minerals are exposed to sunlight and interact with photons. If a sample of mineral deposit is collected from a site in total darkness and then re-exposed to light in a lab, by measuring its luminescence signal we can determine how long it has been since it last encountered sunlight, or since it was buried. It only takes as little as a couple of minutes of light exposure for the electron traps to reset. This is useful because now not only do we not need to rely on organic material, the sediment deposit we find artifacts in can also be dated if they contain quartz or feldspar minerals. Just like TL, we are still relying on the same electron traps to date the samples, so the age range and uncertainties are also 200,000 years at its max, with a minimum of approximately 100 years for younger samples, with a 5 to 10 precision rate. In principle, OSL from any grain size can be measured, but consideration of variations in dose rate, likelihood of bleaching and potential post-deposition disturbance must be considered. OSL is often preferred to date over TL, as there is a higher uncertainty that the traps were zeroed at time 0, when they were buried. But using TL to determine when ceramic pots were made is still just as useful in determining things like time of occupation. There are several variables that decrease the accuracy of this form of dating, mostly to do with estimating the dose rate. As we can assume, the levels of radiation everyday objects are exposed to are not consistent over time and space. Same applies to old archaeological deposits. 1. Cosmic radiation varies by latitude and longitude, meaning that depending on the geographical location, the dose rate will change for each sample. 2. Water acts as a natural water barrier to some form of radiation, so variations in moisture content can also change the dose rate. And 3. Cosmic rays can only penetrate the ground to a couple tens of meters, so depending on the depth of the sediment layer above, as well as its density, the sample will have been exposed to different levels of cosmic radiation. But there's still one more form of trapped charge dating, and that is electron spin resonance. Developed in the 1980s, ESR dating measures largely the same as the previous two methods, calculating the dose received compared to the dose rate generated by surrounding environments, primarily uranium, potassium, and thorium. But instead focusing on substances like tooth enamel and calcium carbonate deposits like stalagmites and stalactites in cave systems. The optimal sampling material for ESR dating should show adequate resetting of the ESR signal and ability to show the surrounding environment's radioactivity, come from an undisturbed deposition, and be of around 100 to 200 in grain size. It's usually considered that the optimum time range for ESR dating of tooth enamel lies between 50 and 600,000 years, with some examples going back 2 to 3 million years, with relative age uncertainties usually sitting between 10 and 20%. But the older the sample, the higher the uncertainty due to uranium accumulation, making most dates beyond 300,000 years very inaccurate. The ability to date the development of tooth enamel allows us to deduce how long the animal or individual was alive for. The dated event in this circumstance corresponds to the development of the tooth. The ability to get an accurate date depends on the assumptions that the sample comes from a closed system that has not been exposed to high temperature or light since its last significant event. Now back to our archaeologist stuck in the desert. He continues to dig down past the grave and finds a deposition layer full of marine shells. There is no sign of human interaction with this layer, so it could be very old. Radiocarbon and Dendrochronology are not useful in this situation, and neither are TL or OSL. ESR may be used to date these shells, but a better method was developed in the late 60s known as Amino acid Racemization, or AAR dating. AAR is used to estimate the age of biological material based on the racemization process of amino acids. When organisms die, their amino acids exist in an optically active form known as a chiral form, or mirror images of each other. As time passes, these L isomers gradually convert to D isomers. This conversion over time allows, just like in radiometric dating, to measure a ratio between L and D isomers that can be used to estimate age. The rate at which this racemization occurs depends on variables like the type of amino acid, the organism's species, the protein shape, and also temperature. This works on marine shells, bone, teeth, making it very useful for dates older than radiocarbon's 50,000 year age limit. If our archaeologist uses this method to date the shells, he will be estimating the time since the organism died and the racemization process began. Today, using modern techniques of AAR dating, sample sizes can be as small as 2 milligrams. The precision can vary, but generally speaking, can get within plus or minus 10 to 20% of the estimated age. Temperature can have an effect on the process, so when it comes to collecting samples, our archaeologist wants to look for something buried under at least 1 meter of sediment, so seasonal temperature variations are dampened to less than 6 degrees. The rate at which original proteins degrade varies, so things like the local pH, burial conditions are assumed to be consistent, unless evidence suggests otherwise. It is also assumed that the sample has remained in a closed system since its deposition, and the initial baseline ratio of L to D amino acids is assumed or can be accurately estimated. The desert archaeologist keeps digging down just below the layer of shells. He finds what he presumes to be an ancient lake bed. It seems this entire area could potentially have been an old lake system. Is it possible for him to date such a situation to put an age on approximately the last time there may have been a lake? As it turns out, a dating technique developed also in the mid-20th century may be of use, called Archaeomagnetism. This method aims to determine the age of archaeological context based on the alignment of magnetic minerals within them, relying on the knowledge that the Earth's magnetic field is constantly changing. When a ferromagnetic material is heated to a temperature above its Curie point, which is the temperature at which it loses its magnetic properties, the magnetic poles within the material get mixed up. But if that same material is then cooled in the presence of a magnetic field, like Earth's magnetic field, the material's poles will realign with that field and will freeze in place in the direction of the magnetic field at the time it was cooled. This is called thermoreminant magnetization. Now when it comes to archaeology, there are many useful examples of materials that have been heated up and then cooled down, like the bottom of a hearth, burned building structures, or bricks from a kiln or oven. All of these will have undergone thermoreminant magnetization and will be magnetically locked in accordance to the Earth's magnetic field direction at the time it was heated and cooled. Over time, it is known that the direction of the Earth's magnetic field changes and fluctuates, with a complete polar reversal happening roughly every 300,000 years, where the north and south poles swap positions entirely. Although this number changes a lot, and the last recorded reversal was the Bruns-Matuyama reversal from 780,000 years ago. So how does our archaeologist actually get a date from any of this? By compiling and analysing the magnetic properties of samples from various locations, and dating them using alternative methods like radiocarbon, it is possible to construct regional master curves depicting the change in direction of the local magnetic field over time for places all around the planet. And then, just like the dendrochronological master curve, we analyse the magnetic field of our sample and compare its direction to that of the master curve to get a date. Now this is assuming that the region you got the sample from has a master curve available, and that the object you are sampling hasn't been moved since its deposition and has in fact undergone TRM. This is why grabbing a few samples from the same spot and getting an average direction is more effective. And if all goes to plan, the dates can be as accurate as 50 to 100 years. Again, master curves are only for recent dates. The oldest curve goes back around 10,000 years. But this dating methodology can be used to date sites that are millions of years old as well. This is done using the pole reversals. While excavating sites, if you are able to identify a point where the sediment's magnetism completely flips, then you can accurately date that to a reversal event millions of years old. Since this method requires the exact position of the archaeological material to be recorded in relation to the present magnetic field, everything must be sampled in situ, and ideally be sampled as a solid piece. Then once north is marked, a piece of the sample is broken off, only about 10 to 20 grams, and analysed in the lab, avoiding all other external magnetic influences. So how can our desert archaeologists use this method? There is no burnt material or human artifacts present. As it turns out, TRM isn't the only way to get a magnetic reading. Depositional remnant magnetization, or DRM, describes a natural phenomenon whereby iron oxide particles eroding from the continent will fall into a still body of water like a lake. As they fall below the water, these magnetic pieces of rock behave like compass needles and align themselves with the Earth's magnetic field. Ultimately, more sediment is deposited over the top, and these aligned particles become fixed in the lake bed. So our desert archaeologist, thinking he is looking at a lake bed, decides to take a core sample, which will show him the development of the magnetic field through time, which he can then compare to a relevant master curve. No heating required, no worries. The magnetic field observed will correspond to the sediment's deposition in the lake over time. Now there is one more way of measuring magnetization called chemical remnant magnetization, or CRM, but this video is already too long, so you can look that up yourself. At this point, the archaeologist is thirsty, deep in the ground, and has no way of getting out of the desert, so he decides to dig a little deeper to get some shade. Upon doing so, he finds a thick layer of volcanic rock and debris. A volcano somewhere in time and space has erupted and left a dark black layer of volcanic ash and tephra deposit over the ground. For this, we can bring back our knowledge of radiometric dating. Instead, this time, our archaeologists will no longer be using the carbon-14 isotopes that everyone knows and loves, but instead potassium and argon. Just like in radiocarbon, when dating something using potassium-argon, we're looking for the ratio between two different isotopes. This is useful over carbon dating because unlike carbon-14, which has a half-life of 5,700 years, potassium-40 has a half-life of 1,250 million years. So by measuring the rate at which it decays into argon-40, we can date much older material. Potassium-argon measures the ratio between the decrease of potassium-40 and the increase of argon-40 over time, with both variables changing simultaneously. And then, just like carbon, from the ratio and the half-life we can determine the age of the mineral formation. To date, using this method, we need material that had potassium-40 and no argon-40 when it formed, as to provide a clean slate for its decay. This includes potassium feldspar, muscovite, hornblende, clays, basalts, and glasses among other things. As it turns out, magmatic minerals contain a lot of potassium-40 and no argon. And even if there is argon, since argon is a gas, as the volcanic material is launched into the air, all of the argon gas escapes, leaving potassium-rich material to spread across the landscape. This dating method is also the only way that tephra shards can be directly dated. Presented with a thick layer of volcanic ash and tephra, potassium-argon dating is the obvious choice for our desert archaeologist to use in his predicament. But even better than potassium-argon dating is the newer, now more commonly practiced argon-argon dating, where a sample is irradiated to convert a stable isotope of potassium-39 into argon-39 as a proxy for the potassium-40. This method tends to give more precise results and has the ability to target single crystals, thereby reducing the extra noise. These radiometric techniques can be used to date volcanic rock between 30,000 years old to the age of the Earth, dating the exact moment these volcanic rocks were formed to a 10% error margin for potassium-rich samples, with the argon-argon dating landing at a higher accuracy of sometimes less than 5%. But there is a problem. What if there is argon-40? How do we know for sure that we only started with potassium? Lucky for us, not only is there argon naturally in the atmosphere, but there is a known ratio of argon-40 to argon-36. So by checking samples for their levels of argon-36, we can accurately assume how much of the argon present in the sample wasn't due to radioactive decay. We also assume when our samples were first formed that there was no radiogenic argon already present, and that from that point onwards there was radiometric argon-40 being lost or gained either, both of which would skew the results. Luckily, both of these assumptions can be tested through a process called step heating, which incrementally heats up different layers of the mineral so you can individually determine the age of each layer. And if there's any funky business going on, then you can assume that one of the assumptions wasn't met. The archaeologist keeps digging down and down, now too deep below the ground to see any daylight, and finally after all this digging hits solid granite bedrock. There's no going down from here, he has reached the end. So how would he go about dating the bedrock? The first potential dating candidate is known as cosmogenic dating. High-energy cosmic rays from outer space bombard the Earth and interact with the atoms in our atmosphere to produce isotopes like beryllium-10 and aluminium-26. Just like the production of carbon-14 in the radiocarbon process, these cosmogenic isotopes, which is the term for isotopes formed from their interaction with cosmic rays, are produced at a known rate. This rate is dependent on things like latitude, longitude, and altitude in the atmosphere. So how do we get a date using this phenomenon? Well, we can through a process known as burial dating. Inevitably, rocks on the Earth's surface are exposed to these cosmogenic isotopes. Over time, these isotopes like beryllium-10 and aluminium-26 accumulate in mineral quartz, while exposed to the atmosphere. When these minerals are subsequently eroded or buried over time, they will no longer be exposed to the cosmic rays, and the isotopes that previously accumulated within the mineral will decay. Since beryllium and aluminium have different half-lives of 1.4 and 0.7 million years respectively, they start to decay at different rates. So once again, by measuring the ratio between the two isotopes, we can determine how long it's been since they were buried. This sort of methodology is perfect to determine the age of things like glacial retreats, erosion rates, landscape evolution, and even able to sometimes date rock art. The same concept can be applied to cosmogenic exposure dating, where instead of seeing how long a surface has been buried, you are identifying how long it has been exposed to cosmic rays at the surface. Typically, 20 to 100 grams of quartz is required for an accurate measurement, so generally a large sample of the original rock, maybe a kilo or two, is brought back to the lab. Depending on the isotope, cosmogenic dating has been used to date things from 1,000 to 10 million years old, with a precision of roughly 5%, although dependent on the isotope and sample quality. But the older the sample, the less effective this method becomes, due to uncertainties in the initial assumptions that are made on things like stable isotope reduction and exposure rates, mineral disturbances, and accurate knowledge of burial depth. If our desert archaeologist suspects this piece of bedrock is much older, he can turn to one last dating method: uranium series dating. I'm officially out of time, so I'm going to have to do the rest of this video by recording, and I'm not going to do any more animation, but there's only one more dating method left. The basic principle behind U-series dating is the same basic principle that we've been using for radiometric dating principles this entire video. We have one radioactive atom of uranium-238, which will, through multiple steps this time, not just through one step, through 14 steps, eventually decay into lead-208. The reason this is useful in this situation is because uranium-238 now has a half-life of 4.5 billion years. So rock as old as the creation of the Earth can be dated using this methodology. So what this is saying is the more lead you have in any specific rock sample, the older the rock is. But we know for a fact that lead, on average, is lighter than uranium. So when you are counting the ratio between lead and uranium, you have to take into account that for every 238 grams of uranium, there is only 206 grams of lead. So by taking into account this ratio, we can use this to backdate and figure out the age of the rock itself. This method is typically applied to rocks that have trace amounts of uranium already present, like zircon, titanite, and apatite. For example, the oldest dated rock in the world was dated in Australia, which was a sample of a zircon crystal using uranium lead dating. This date range can age from 1 million years to 4.5 billion years, being the half-life of uranium itself. So it is quite reliable, broad, useful dating method to use in a whole wide variety of situations. What we're dating in this situation is the crystallization of the minerals inside the rock. So if we're dating zircon minerals, then we are dating the moment in time at which the zircon minerals formed. Generally speaking, most samples that are collected must be free of any contamination and only require about 0.1 to 0.5 grams to be sufficient for analysis, although larger samples are also useful in this situation. This is a highly precise dating methodology, with younger samples' precision typically ranging from 0.1 to 1%. Older samples, going back to several billion years old, can range from 2 to 3% in uncertainties. Just like our other radiometric methods, we are assuming that this sample came from a closed system. We are assuming constant decay rates over time, as well as no initial presence of lead-208 already in the sample, and that there is no evidence of contamination post-deposition of the mineral we are looking at dating. It is also important for actual measurement in laboratories that there is a sufficient amount of uranium to begin with. This is why larger samples are generally a more safe bet. Thank you for watching. Sorry this video was half an hour long, but I hope you enjoyed.